All right, so we're going to get started with our first, or I guess our 0th lecturette on advanced integration techniques. This one's just going to sort of get us, get us started, get us thinking a little bit. There's not really any new techniques here. There might be some clever implementations of old techniques, but I don't think there's any like real groundbreaking techniques quite yet. I really just wanted to get you sort of familiar with like the fact that, like, I guess if there's one thing that you could take away from this, it's that the rules that you're taught in, say, Calc 2 only apply to well-designed problems, and a lot of problems aren't well-designed. They're real-world problems, and so they're, less clear-cut. So that's sort of the idea for today, is I want you to try and sort of understand that. The other thing I want you to see is that definite integrals can be really nice. Sometimes when you get to the end, like the form might be very, very nice. There might be a lot of simplification, even if it looks very complicated. There's often ways that you can simplify the problem down a little bit. So why don't we get started with that? So we've got this integral here in example 1. And I should also note that anytime you see a constant here, I think throughout we're using a, at least so far, it's always a positive constant unless it's otherwise specified to be something else. And the other piece to it here is that it's constant with respect to the variable of integration. So we're assuming that there's no like connection there. So example 1, evaluate the following integral. So we're given this integral from 1 to infinity, and we've got a quotient here as our integrand with respect to x. I'm going to do a substitution, and this is a really sort of clever substitution that you might not see immediately, because it is definitely a weird one. I'm going to set, so what I'm noticing is that we've got this x minus 1 inside of a root. So I'm actually going to set t squared equal to x minus 1. And yeah, we can do that. It doesn't have to be a function of one variable or the other explicitly in that sense. You can sort of, now this is a function of x, but it doesn't have to be that direct. You can kind of play with these manipulations in any way you want. So what this means is that 2t times dt is equal to dx, which is quite nice. Maybe we'll change our bounds. So if x equals 1, then that means that t is going to be, so x is 1, x minus 1 is 0 squared 0. And if x is infinity, then we're still going to get infinity for t. So we've changed our bounds over. And we can rewrite this integral. Now, throughout this course, I'm going to write I to just be whatever integral we're trying to solve at that point. So we've got the integral from 0 to infinity of, and now let's start replacing things. So we know, first off, that square root is going to be square root of t squared. So I'm just going to write that as t. And then the x plus a, we know x is going to equal t squared plus 1. So we get t squared plus 1 plus a dt. And I guess I got to deal with that too. So we'll have 2t dt. I'll move some things around. So I'll maybe pull the 2 outside. And I'll also cancel out the t on the top and bottom, so that we're just left with dt over t squared plus 1 plus a. And I'm going to do another sub. I'm going to let b equal 1 plus a square rooted, if I can write that. 1 plus a. And so what we'll get then is that I is the integral from 0 to infinity, 2 times, of dt over t squared plus b squared. And you might recognize this integral as a trig integral. And so if you solve this trig integral, this is, maybe I'll write this down because it's actually a relatively important antiderivative to sort of know, is if you ever see like dt over t squared plus c squared, something like that. That's equal to so it'll be 1 over c times the arctan of t over c plus constant of integration, big C. So, if you ever see that, that's a quick integral to be able to do. Oftentimes these things come up. So what we'll do is we can write out our answer. So it'll be 2 times 1 over, so in this case our C is B, arctan of t over b, and our bounds here are from 0 to infinity. And we can simplify this out a little bit. We'll get 2 over b times, and maybe I'll write out what b is. We know b is square root of 1 plus a, square root of 1 plus a. And we have arctan of t over square root of 1 plus a on our bounds. And so maybe what I'll do from here is we'll start plugging in. We get 2 over root of 1 plus a. Now arctan, so what we have here, and I guess I should, if I want to be formal with this, we should do like limit as b approaches infinity, and write infinity, there we go, of b over root of 1 plus a minus, oh, and pardon me, this should be in an arctan. So let's put that in arctan, minus arctan of 0. Now arctan of 0 is just 0, so that cancels out. And you might know that the limit as arctan goes to infinity is pi over 2. So what we have here is 2 over root of 1 plus a times pi over 2, which is just pi over root of 1 plus a. It's kind of interesting how nice that turned out to be. At the end, we just get, pi popped out of this, which maybe that's kind of surprising because it doesn't look like there's anything pi related, like circles or triangles or anything going on here that would make you think of pi. There is, as we've sort of seen, the tan sort of pops out of nowhere. But yeah, that is the area under that curve. And the nice thing about using these parameters like we have, having a here, is that if we ever see an integral of this form, we can just jump to the conclusion just by plugging in an a value. So we've kind of solved more than one problem just by parameterizing it. Example 2. So example 2 here, we've got an integral 1 over 1 plus e to the ax. Kind of ugly again. Yeah, you might stare at this for a little bit and think, oh, if only there was a quotient rule. Hint, hint, there is a quotient rule. But anyways, we'll leave that for another time. So I'm going to set u equal to e to the ax. And then what we get is du is going to equal a e to the ax dx. So in other words, if I rearrange this, I'll get du over au equals dx. Notice that e to the ax is equal to u, so I just changed that to be a u. And maybe I'll do my bounds. So if we do u at 0, so I want to make sure I do this right, yeah. U at 0, or I'm going to write it a little bit better. If x equals 0, then we're going to do u to the power of, e to the power of 0, which is 1. And then if x is infinity, of course, we're going to get u equals infinity. And I shouldn't have just said of course, because you might say, well, what if a is negative? A is not negative. So it's always going to be a sort of positive, like exponential growth curve. Anyways, we can write this integral now. So we get our integral is integral from 1 to infinity of 1 over 1 plus u. And then we're going to multiply that by du over AU, something like that. All right, so that seems fine for now. Maybe I'll bring the A on to the outside here, since A is a constant. So this will be du over u times u plus 1 plus u, sorry. And from here, maybe you sit and think with it for a little bit, and you don't see anything because there's not sort of any nice subs here that you could do. The best you can do is partial fraction decomposition. So if we do partial fraction, what we get is 1 over a times integral from 1 to infinity of 1 over u du. And maybe I'll just write that as du over u. And then minus 1 over a integral from 1 to infinity of du over 1 plus u. So that's our partial fraction decomposition. And at this point, we can integrate. And so we'll get 1 over a times ln of u minus ln of 1 plus u. And we don't need the absolute values here because our bounds are always positive. But we look here, our bounds are always positive. Absolute value is not going to make a difference. We can simplify this out a little bit using properties of ln. So this is u over 1 plus u inside the ln. Got to keep our bounds. Easy to forget about bounds. You know, they commonly sort of get dropped, unfortunately. Now this is an improper integral. So we can do the limit as b approaches infinity of, well, maybe I'll bring the 1 over a to the outside. So our integral is 1 over a times the limit as b approaches infinity of the ln of b over 1 plus b minus, if we plug in 1, we get ln of 1 over 2, something like that. And I believe what we can do here is if we do this limit, of course, we can swap the ln and the limit sign. And minus, so ln of 1/2 is negative ln of 2 using properties of our logs. So we can do that. And I believe if you do this, you get ln of, you could either like divide by the highest common, or so the highest power here, or you could do L'Hopital's rule if you want it to be overkill. You get 1. Ln of 1 is 0. So what we're left with is ln 2 over a. And that's the answer. Also fairly simple, right? It was nice that we were able to get it so simple and there wasn't a big giant expression, right? And please leave it as exact. Don't change it to decimal. That would have just made everything so ugly. All right, example 3. So we've got a ln here, an integral of a ln expression. We're going to use integration by parts. So what I'm going to do is I'm going to do, let's let u equal the ln expression. And then that means du is going to equal, now this is going to get really ugly, so maybe I'll have to move some of this a little bit over here. It is going to get super ugly because we're going to have to do a chain rule. If you do chain rule, so derivative of ln is 1 over, so we'll keep the inside the same. And then derivative of that inside is going to be a squared over x cubed times negative 2. Right? Yep. Which is ugly, right? Like there's no way around that. And that's times dx. Now we can simplify this a little bit, which is going to help. So we'll get negative 2 a squared over x cubed plus a squared x dx, like that. So that kind of simplified, but it's still pretty ugly. Let's do our super easy dv equals dx. then that means, v equals x. So we've sort of, that's a typical by parts thing you would do to solve lons, right? You might have done that in a previous course. Anyways, we can keep going here. So we've got our integral from 0, and do I want to change the bounds? Yeah, sure. Let's change the bounds. So, sorry, we're doing by parts. We don't change bounds for by parts. We do ultraviolet voodoo. So our integral is going to be ultraviolet voodoo. I should write an I here somewhere. So uv is x ln of 1 plus a squared over x squared. And then integral of minus integral of v, which is x du, which is this giant expression we wrote up there. So maybe I'll bring the 2 to the outside, so we'll get plus 2. I should also keep my bounds here. It's easy to forget, like I said. This is an A in case you can't read my writing. Anyways, so we have this. And I guess I can bring out the a squared as well. And what we're left with is dx. Well, dx is, we want to change, let's see here. Yeah, so we've got an x on the top. That's our v. And then du is going to be this whole over x cubed plus a squared x dx. And we can simplify that fraction a little bit. So that means our integral is x ln of 1 plus a squared over x squared on these bounds plus 2a squared times our integral of dx over x squared plus a squared. And this integral, like we did earlier, is arctan. So a squared over x squared on our bounds plus 2a squared. And yeah, this we said was that special arctan relationship. So 1 over a times arctan of x over a. So we get that on our bounds. So we've got this. I'm going to start by by separating this piece here, because I think that's probably the easiest method. So we're going to do the limit as, well, let's think through this. Let's take the limit as b approaches infinity of this term, b ln 1 plus b squared over x squared on our bounds. Oh, sorry, pardon me. That is, we are plugging in the top bound here. I'm going to change this limit by doing a simple substitution. So I'm going to let b equal 1, c, b equal 1 over c. And so what we get then is the limit as c goes to 0 from the positive side of 1 over c times the ln of 1 plus c squared x squared. Pardon me, there's something wrong here. This should be a squared over b squared. So then we get a squared c squared, like that. Perfect. Because we were substituting b in for x to do this bound. We can write this as ln of 1 plus a squared c squared over c. And the limit of that as c goes to 0 from the positive. We can apply L'Hopital's rule to this. If you try plugging in 0, you get 0 over 0, which is not going to be pleasant. So we'll use L'Hopital's rule, and we're left with the limit as c goes to 0 from the positive side of, let's see, 1, I believe we'll get a squared c times 2 over, and I'm just doing chain rule on ln of 1 plus a squared c squared. And c, of course, on the bottom goes to 0. Oh, sorry, goes to 1. Now if we plug in 0, you can do the whole, divide by the highest power, and you're going to get 0 as your limit for this. So that means we got the top bound. Let's see if we can figure out the bottom bound. We plug in the bottom bound, so we were going to 0 from the positive. A lot of our math is going to be the same. So we'll do a swap here and make this C. And sorry, this should be C goes to infinity now because we're doing 1 over. And so we'll write this as a fraction. We'll use L'Hopital's rule. Sorry, that's infinity of 2a squared c over 1 plus a squared c squared. And if you plug in infinity here, you have infinity on the bottom. So this whole thing is going to go to 0 as well. Very nice. Yeah, it's pretty great. So from here, what we can do is so since we know that the top bound is the 0 and the bottom bound is 0, we can get rid of that whole term. We can get rid of this whole blue term. And so all we're left with is 2a squared over a. So I'm just going to merge those together. So 2a arctan of x over a on our bounds. Now those bounds, how do we deal with that? You might be wondering. Well, we can plug them in. And so we'll get arctan of infinity. Arctan of infinity, I'm going to sort of skip out the limit step here, but the limit of, say x goes to infinity of arctan of x is pi over 2. So if we plug in infinity into arctan, you can think of it like that. It goes to pi over 2. And if you plug in 0, you get 0. So we get 2a times pi over 2, which is a pi. That simplified really quickly. That was a sort of intense big integral, and yet it like collapsed down to a pi, right? Super easy. So now anytime you see an integral of that form, you can simplify it right down. Example 4. We've got this integral here, and oh boy, does this look ugly. And it is. I'm not going to lie to you about that. It is pretty ugly. What I'm going to do is I'm going to start by taking that integral. I'm going to multiply both sides by x root of x. Sorry, x to the power of root 2. And I wrote that wrong, x to the negative root 2. So I'm just going to do this. Multiply my integrand. I'm really multiplying my integrand by 1, so I'm allowed to multiply anything by 1. I'm just writing 1 in a really weird way. So, and I'm allowed to do this as well because that term is never going to be 0 over 0. We don't have to worry about that. So I can write this out, sort of expand this, this product here. We'll get x to the minus root 2 on the top. And the bottom, we'll get x to the 1 minus root 2 plus 1 dx. So we've definitely made some progress here. Let's do a u sub. I'm going to let u equal x to the 1 minus root 2 plus 1. So the whole bottom. That means that du is going to be x to the minus root 2 dx, which is nice because we have that. And that's why this multiplication by this factor worked out really well in our favor. Might seem counterintuitive, but it worked out really well. I'm going to leave the bounds in terms of x because I feel like it's easier for this particular integral. So we're going to leave it as x is root 2 and x is infinity. So what we'll get is that whole top, that blue thing is going to be du. And on the bottom, we have u. That's easy, isn't it? Ln of u. From x equals root 2 to x equals infinity. So that is ln of x to the 1 minus root 2 plus 1 on our bounds. And I don't need to write x equals anymore because that's the only variable left. And let's see how this will work. So notice that 1 minus root 2, that's going to be a negative number. So that means we've got x to the power of a negative number, which means our limit as we go to infinity is going to approach 0. That means we're going to get ln of 1 minus, because this will go to 0 when we plug in infinity, then minus, if we plug in root 2, we get root 2 to the 1 minus root 2 plus 1, like that. And I don't think I'm missing anything. I think that's right so far. And so what we get is, hopefully I'm doing this right. I made a mistake, yes. Something's going on here. Maybe you were shouting at your screen. I forgot to, when I was doing my power rule here, I forgot to, to multiply. There should be 1 minus root 2 here, which will change my integral over here to 1 over 1 minus root 2. That, which means this will be 1 over 1 minus root 2 times that. 1 over 1 minus root 2. And simplify this side. 1 over 1 minus root 2 times this whole thing. And so I think ln of 1, I know ln of 1 is 0. And so what I'll get is negative ln of root 2 to the 1 minus root 2 plus 1 over 1 minus root 2. Now, is this as nice as the other ones? No, by no means. Is there a way to simplify this? Maybe. I can't see one, but there probably is some really elegant simplification that I'm just not seeing. This is probably where I'd leave it. Is it ugly? Yeah, not all of them are going to turn out so nice as that last one, a pi. But, nonetheless, it's still interesting. We'll do one more here, example 5. And we're asked to recall a couple definitions here. So maybe you've seen this before, maybe you haven't. But these are the hyperbolic functions. So the hyperbolic functions, we pronounce these as cosh and sine, or hyperbolic cosine and hyperbolic sine. And they're defined like this using exponentials. So there's other definitions you can use that involve actual hyperbolas. So in the same way that trig expressions are defined on circles, on the unit circle, hyperbolic functions are defined on what we call the unit hyperbola, which looks something like that. So it's slightly different. Kind of feels like it's like the opposite in a way. Anyways, we'll keep going. So if I use this definition of cosh, I just wanted to include this in here so that you could see how cosh kind of works. And it's also a neat substitution. So I do 1 over cosh, that's going to be 2 over e to the x plus e to the negative x dx. And I can bring the 2 outside, which would be nice for us to do. So e to the x plus e to the negative x, like that. And I'm going to do a u sub. Let's let u equal e to the x. Then du is going to equal e to the x dx. So du over, or maybe I'll write it as e to the negative x du equals, I don't know, you know what, let's write it as du over u equals dx, since we know that u is equal to e to the x. And I should be able to keep going here. We should also plug in our bounds. So u at infinity is going to be infinity, since e to the infinity is infinity. And u at negative infinity, the limit as you approach negative infinity of e to the x is 0. So we get this. Got our 2. And so we'll get 1 over u plus 1 over u times dx is equal to du over u. We can expand that out. We get du over u squared plus 1. Oh, that's nice. We've probably seen that integral before somewhere. That is just arctan. Arctan of u on our bounds. And so from here, if we plug it in, we get arctan of infinity, which I guess I can just write out, is pi over 2, minus arctan of 0 is 0. So we get 2 times pi over 2, or just pi. Isn't that nice? Nice sort of more pleasant integral to end our lecturette with. So if you have any questions, feel free to let me know. Hopefully this was able to give you, like, the key takeaway here is that, these integrals, sometimes they're easy, sometimes they're hard. Oftentimes they simplify to something that's more elegant in a way. Parameters aren't a bad thing to be scared of. Sometimes you can do clever substitutions. So there's a lot of little key takeaways I want you to get from this section. There's going to be some homework problems that you can try. So feel free to do that. And yeah, if you have any questions, feel free to let me know. Hopefully that was helpful.